What they do in Hollywood. Assignment number 9, take 2. Yeah. Take 2. Alright. That looks better. Only assignment for CAM number 1. The title of the drawing is going to be CAM displacement diagram. Now, what height of text would I expect you to provide me in the title block for the title? What height of text? This is a 1-to-1 scale.
Half inch.
No. What?
5/16?
Nope. Half of that.
5/30 seconds?
5:30 seconds. There you go.
I know it was a 5.
Boy, the other class got that a lot quicker. All right. The drawing number is going to be KIN 255-9. What height of text would I expect you to provide me in the title block for the drawing number?
8.
Yes, 1/8. Very good, Eric. Thank you very much. Then the scale can either be full or none. It's not really a scalable drawing per se. It's a diagram more than anything else. And what height of text would I expect to get from you for the scale? 1/8 is acceptable. I will also accept 3/32 of an inch height for the scale in the scale block on the title block. And then your date, your name and the date, and what height of text would I be expecting you to provide me for your name and the date?
Small.
Small.
Is it 3/64?
Yes, that is correct, Stephen. 3/64. Now, with all that information and those questions being answered, I would expect not to have to deal with any corrections for that. That's the plan. Okay. There are 2 different scales that you are going to need for this drawing, which will be explained in detail as we progress through the lecture portion. You're going to find them on the M drive, the CAD folder, the CAD 255 kinematics drafting folder, AutoCAD drawings folder. There's one that's going to be called harmonic motion scale and one that's going to be called uniformly accelerated and retarded motion scale. Those will be inserted into your drawing and used to generate the diagram, which would ultimately be used to create a profile of a plate cam that would be used to provide motion for something else. You can also access these 2 drawing scales out of D2L if you're away from campus. And the drawing is going to be done on a B-size drawing, and it's going to be due at the start of class on Thursday, May 25th. So now we have all that correct information, and the previous FUPA I can delete off of the camera, and those that are watching the video will have no idea that that happened. And if you go back and review that as well. All right. That's the, and then just so that you are reminded of it, there's going to be a lecture on assignment number 10 on Thursday, May 25th. Any questions on that? Except for the fact that maybe you don't have enough information yet to know what to ask for a question. We'll get to that.
Here is a purple
All right. So I'm going to go back to my mechanics DVD and run through some cams. There can be more shapes than this, but basically can be categorized as a pear-shaped, a circular, a heart-shaped, a box cam, and a linear cam, which, other than the linear, will take rotary motion and convert it into linear motion. So what is a cam? A cam is a specially shaped piece of metal or hard-wearing plastic, which is usually fixed to a rotating shaft. We've discussed shafts when we talked about gears, but I'll just pull that up again. Things like gears, pulleys, and now cams can be attached to a shaft with, they love to call it grub screw, I call it a set screw, or it can be a key and a keyway. This is a give head key, it can be a square key, it can be other types of keys that will hold it. It's a mechanical connection. Now just to remind you, if there's a square key in the shaft and the cam, half of the height of the key goes in the cam and half of the height of the key goes into the shaft. All right, I think I've already shown you this. It can also be a spline type of a situation that gives a lot more positive connection between the motor. So right here I have a cam. This is a pear-shaped cam, and I also have a follower on it. So I'm going to back up here and take a look at a circular cam more than a pear-shaped. So I have followers. A circular cam is also known as an eccentric cam. The center of rotation of the cam is offset from the geometric center of the circle. This type of cam produces a smooth form of motion called simple harmonic motion. So as the follower has some kind of motion to it, which can be connected in turn to linkages to make other things operate, that's what gives us our kinematics. It's a study of motion and linkages and connections. As the cam is symmetrical, the rise and fall motions are the same. This type of cam is often used to produce the motion in pumps and to operate steam engine valves. So this DVD just loves these little steam engines. I think it might be because they're very simplistic in nature and there's not a lot of complication to it, and it's very easy to see the motions that are going. And we don't need all that extra noise here. So as we look at it, it's off-center and it has a constant motion to it that is very smooth. This is an oil cup in here that would the top would screw off and you'd put in a viscosity of oil that because this is rotating in here. And it looks like it's up. I did that yesterday too. Flipped right as my pointer went up there. Operating some kind of little pump mechanism up here on the tractor. I think that's a tractor. Maybe not. It's power or some sort. All right, and then another circular cam. This one's just a little slower. Operating. So here's our split bearing in here, and there's a grub key or a gib head key. And you can see that the motion is very smooth and consistent in its operation. I think another reason is it's got a lot of big stuff here and it's really easy to see. Alright, so let's stop that. Alright, and now we have different shapes that are associated with our follower. This is a round-headed follower. And if we put this in motion, because it's eccentric, it's out of the center, you have this pretty much constant up and down motion with the follower, and it connects to something. It's part of the design. We can change what the follower looks like. I can use a point. My guess is that would be more of a wear factor, or it might wear groove in the cam itself. But there must be a reason for it because they do exist, and you can see those examples in the textbook as well. Here's a flat follower. Has its own purpose, spreads out the forces, doesn't do quite as a concentrated wear as other follower ends might. And then a roller. Yep. Would be probably maybe the best because you've got rotational value going on in here and you've got rotation going on here, and it's going to probably wear the least amount because you've got two moving parts here. Then we have pear-shaped cams. Pear-shaped cams are often used for controlling valves such as those found in car engines. This type of cam has a long dwell period during which time the follower does not move. So when a cam design or diagram calls for dwell, there's no rise or fall in the follower itself, and it stays in its position. When the follower is moving, the rise and fall times are equal because of the symmetrical shape of the cam and the fact that it's centered on the shaft itself. Now, I can have a single mechanism going on. This is a video of a pear-shaped cam that has two roller followers on either side of it, and it's got springs that are gonna pull it back in. Some of it's gravity in the follower. It raises up and then comes down on its own. Others have mechanical applications to return them to the position. So we've got some cast iron pieces in here and roller bearings, and you can see that it's operating something. They don't give us the view of what's going on. All right, so a dwell period with a pear-shaped cam looks like this. You're gonna have a dwell period where it doesn't do anything, and then when it comes around to where this actual lobe is on there and it's centered around that, you get a uniform rise and fall out of that. So if you've ever rebuilt an engine in a car and your valves have a camshaft, and it's gonna raise and lower them in timing with the rest of the cycle of the 4-cycle engine. So you have a follower, you have a certain amount of stroke, a certain amount of rise, and a certain amount of fall, which is the same, and then a dwell period, and it's generally a clockwise rotation. So dwell is the point on the profile of the cam where the follower does not move. Stroke, the distance between the highest and lowest points. Crown, the highest point on the cam, and heel, the lowest point on the cam for terminology. And if we change the shape to round, then you're gonna get a motion that's undulating more than rising and falling. So it's up and down, and again, it's kind of based on the what's going on. And if we change to a shape that's more heart-shaped, you get kind of an abrupt start and stop at this point and at this point, because there's no radius, no transition, smoothing in and out of the motion. Again, there may be a purpose for why it's going to do that and rotate in such a manner. Yes, no.
So you can, it looks like you can get any waveform you want by carving the shape of the cam.
Well, you might be limited in some degree, but pretty much there's a lot of motions, different motions that are generated with cam design, and we're just kind of sticking with the basics here. But yeah, that's kind of got some truth to it. And then a heart-shaped cam, we've already kind of looked at the motion on that. So if I have a round follower, I get kind of a start and stop at 2 different points, and then a rise and a fall. If I have, now I don't know why I would put a flat in here, but if I did put a flat follower in here, it's not going to hit down in this very little shallow recess of the heart shape there. It's going to kind of almost be negated. So that's got something to do with it as well. And then if I have a point, it's definitely going to be in there for that motion. Yes?
So the text says that heart-shaped cam is used in sewing machines.
Yes.
Would the spindle be sort of pressed against the cam by a spring, or would it be gravity that keeps it from?
Somewhere in here I have my sewing machine example, and I've got to try to find it. Oh, maybe it was under reciprocating. So here's your sewing machine, and this looks more like a pear, almost like a pear-shaped cam. But as the motor turns, and it's connected in here to the linkages, so my rotating action is translated in here to a linear or reciprocating motion. And it's probably a little more sophisticated inside nowadays, but you know, when Singer invented the sewing machine, that's the basic principle. And it really hasn't changed over the years significantly, I don't believe. And that little loop up there would be where thread would come through and go through the rest of the sewing machine mechanism and come into the needle. There's a bobbin underneath, and it talks a little bit about a bobbin shape and a heart shaped cam that rotates that. And the two pieces of thread come together and interlock, through the mechanism, and that's what allows the sewing machine to operate. So they talk about it here, and talk about a jigsaw as well that has reciprocating motion to it. A box cam. A box cam has followers that are guided by a groove, machined or molded into the face or edge of the cam. The shape of the groove controls the range of movement of the follower. Box cams can be found on winding mechanisms of fixed spool fishing reels. So that's what keeps your line technically even until you get a snag and it, releases and you get what's called your little bird nest of a fishing line. And then that makes you, yeah. And then the linear cam. Linear cams have reciprocating motion as both the input motion through the cam and also as the output motion through the follower. So there's going to be motion in the cam back and forth, and the follower then is going to be up and down. This one just cycles through. This would be an interesting machine if it could actually do this, but I don't think it's possible without something else going on. So that would go one to there and then back and forth.
So your car is technically a linear cam.
Yeah. Sometimes used on automatic machine tools to control the movement of tool heads. Oh, stop. So that's basically it, and then there's more information as well in the textbook, which again, it would benefit you to go back and take a look at. All right, in designing our cams, we're going to have on page 88 in the textbook in chapter 22 is this, in which it talks about basically 6 different motions that are generated. So they're pretty consistent with, and I'm thinking that there's got to be probably some software out there that would do a lot of this design work. With all the software that exists in the world nowadays, I can't imagine, but we're going to use our just tried and true AutoCAD and do a 2D drawing of this. So if I have a uniform motion in the rise and fall of my follower, this is going to be like my heart-shaped cam. It's going to start and stop rather abruptly, which may be a desirable feature, but lots of times not. If that's the case, then I would go down to my modified uniform motion. The rise and fall, or the follower displacement, is going to control what this radius is that comes in and out of this motion. So then you're going to smoothly come into it and rise up and kind of smoothly come out, rather than a motion that's more abrupt like that. Basically, whatever this height is, let's just say this height is 1, then your radius in here would be at the halfway point or a 1/2 inch radius to transition in and out of here. I might have a parabolic construction method that has some formulas in here about creating the arcs to get in and out of the displacement. I have a parabolic motion, which is also defined as the uniformly accelerated and retarded motion. It looks kind of like my modified uniform motion, but this has got more of a straight line in here, so it's got kind of a constantly different kind of move to it. Again, just depending on what the design needs to incorporate. I have harmonic motion, and I have cycloidal motion as well. And there are different ways of calculating out what these radiuses are based on the rise and the fall of the follower itself. So you can go back and look at some more information. Well, let me go to the actual assignment page. Talk about that for a minute, and then come back. All right. You're going to do cam number 1 as a displacement diagram. So it's gonna rise 2 inches in 150 degrees with harmonic motion. It's gonna dwell for 45 degrees. It's gonna drop 2 inches in 120 degrees with uniformly accelerated and retarded motion or parabolic motion. It's gonna dwell for the remainder. The displacement diagram is gonna be 2 inches high. That accounts for the rise and the drop. And it's gonna be 12 inches long. That 12 inches is kind of an arbitrarily determined figure. I don't think it relates to anything at all.
Would that describe like the circumference of the entire
Yes,
cam?
that would describe the circumference. So we're basically going to take our circular object and do a flat pattern of it as a 2D drawing. Yeah, they actually do show back here in the textbook what those diagrams look like. It might look something like this down here. Now that's fairly complicated. It's got a harmonic rise, a parabolic rise, a modified uniform drop, and some dwell periods. And that's what we're basically going to be creating. Now, there's a certain amount of vertical segments that go along in that. And if you were going to draw this by hand, or actually draw this by AutoCAD, get it situated here. Oh, actually, let's pull this page out. You would actually measure this out of the textbook with a scale and mark off what the actual increments were and create your scale based on whatever the motion was. So if I were creating my harmonic motion scale, I would measure this and I would find out as closely as I could to maybe a 64th of an inch, okay, you know, or 30 seconds. That's like about 3 seconds. And I would have to literally make up a scale, put a horizontal line in, put points on there, and use it as a referencing to determine where that is going to be projected across into my cam displacement diagram. Fortunately for you, I'm really a nice guy, and I have created those and placed them for you to be able to use. Which means that your diagram is going to end up looking something like this. And there is that PDF of this sample drawing in D2L for you to look at. There's also one up on the board now that you can come and take a look at. So what you will end up doing is making a 1-to-1 size, 2 inches high and 12 inches long. You will put in, as text, 0 degrees, 150 degrees, 195 degrees, 315 degrees, and 360 degrees. The height of the text on your drawing, the height that I would expect you to provide me with on the drawing would be what height? 0.10, yes. And what font would be used? Arial. And bold. Excellent. So I shouldn't have to make any corrections on that. You should have a text style already created in your drawings. I'm just checking. All right, as a dimension, you are going to put in here a linear dimension, and you're going to override the text and put in here rise 150 degrees. What keystrokes do you use to get the degree symbol in AutoCAD? %D. Very good, Eric. Yes. So I shouldn't have to correct that. And then you're going to say harmonic motion, dwell 45 degrees, drop 120 degrees, uniform, accelerated, retarded motion, which can be abbreviated UN dot, ACC dot, and like that, and then dwell. And then this vertical dimension here. The ones across the top I will explain. Verbal instruction. You do not need to put those dimensions along the top on your drawing. In fact, I will mark you down if you put those dimensions on your drawing, because that's only for explanation purposes. Questions on that? Yes, Pierce.
So I noticed there's like two sections to dwell in this cam.
Yes.
So is this like more than one cycle, or like not cycle?
This is one
period?
complete revolution of 360
Okay.
degrees.
Okay.
So as it starts out at rest, let's say, it's now going to rise with harmonic motion for a rotation of 150 degrees. and then it's gonna stop and just stay there for the next 45 degrees of rotation. And then when it gets to the next 120 degrees, it's now going to drop and come back essentially to the starting point and then not move from that point on. So it's gonna start here, it'll rise, stay there, and then drop down again for that.
So this thing is like a weird shape, huh?
It gets to be a little bit kind of interesting looking, but it's pretty simple. If we actually created an actual cam off that. All right, now here's how this is going to be constructed. Also, these are kind of construction lines in here. You should use a layer or create a layer that has a 0.13 millimeter line weight. I would like to see them, because then I can check to see if your construction goes, but those should be kind of like hatching line weight. Lighter than your dimensions would be visible. This actual profile line that we're going to create, this is a spline. It's a spline from here to here. This is a straight horizontal line segment, another spline down to here, and then a line segment that is horizontal. That should be on a layer that has a 0.53 millimeter line weight. So there's your verbal instructions that go along kind of with your written and your visual, which again happens a lot in industry, and I'm trying to get you ready for that because you're about ready to get out there. And I'm getting inquiries from a number of folks. There's some jobs up here that have come in. I've had a request from Aerotech. Hey, you got, top-notch, got drafters coming out. I'm interested in connecting up with them. I think they want the finder fee or whatever, but anyway. Nolan,
What was the first line weight again?
0.13.
Thank you. That's what.
0.13. Okay. Right. How do we create this? We're going to use the harmonic motion scale as an insert into the drawing, and then do some things with it. One thing that you should probably be aware of in setting up some parameters on your drawing, because we're going to be using points, it may or may not come in that way, is to check your utilities up here in your home ribbon. Go into utilities and check your point style. The default point style when AutoCAD starts up is a dot, which will never show up. A cross or an X would be two of the main choices that you would want to use, because you're going to have to do some dividing and make equal increments horizontally to match up with the vertical increments that are created using the motion scale. Alright, so check that. Make sure you got that going. You may or may not want to change the percentage size of it on your screen. Again, default is 5%, and sometimes that can look kind of big. So you might want to check that and kind of dial that down a little bit so that you can see what's going on, just as a word. Alright, so here's what I'm going to do. I'm going to do an insert command. And I'm going to browse and go to the M drive, CAD folder, CAD 255 kinematics, AutoCAD drawings, and find my harmonic motion scale and open it up. It's going to be a 1-to-1 insert to match the diagram. I'm going to say OK. You should not get this dialog box that pops up. I used this in class yesterday. I've used it in previous years, and I've inserted this particular block time and time again, and so it asked me to redefine it. You are generally pretty safe in redefining a block as it comes in. It just means that you might have reinserted it previously. All right, so I'm going to object snap track from the baseline of my diagram. I'm just going to snap that, and what I want to do is just drag it out here so that you can see what's going on outside of my title block here. You don't need to do this quite so far out. The other thing is you don't really need to explode it, but I'm gonna explode it so that I can show you a couple more things out of this. So it's individual pieces of geometry. All right, now, let's get this on the screen here. I need the endpoint of this line to match up with the bottom of my diagram. And I need the top part of this line to be rotated at an angle that would leave the bottom of the line even with the base of my diagram, and the top to be in line with the amount of rise that I have in my design, which just happens to be 2 inches. So I need my line to be rotated so that it ends up looking like that. Anybody got any guess as to how many degrees I need to rotate this horizontal line to get it to look that way? You don't? Nick does because he was in here yesterday. You need to calculate it using some trigonometric functions. Trigonometry, oh no, it's pretty simple. And so I'm going to run you through that to show you how you figure that out. And just relax, it's not difficult. So let me blank the screen first. Pull this up. Oh, here it is already, left over from yesterday. That'll help. I don't have to rewrite everything. All right. I will have a diagram that's going to have a horizontal line that will be 12 inches long, and I have a vertical line that will be 2 inches in height. That equates to the rise. Now the rise could be 1.5 inches. The rise could be 1. The rise could be 3, which would change my numbers. In this particular case, the design is set up to be a rise and a fall of 2 inches. That is going to create a vertical and a horizontal line, which creates a 90-degree angle in here. I now will be creating a right angle triangle, which has one side of the triangle is 2 inches in length, and the hypotenuse of the triangle is 3.6875. How did I get 3.6875? That's the length of the line of the harmonic scale as I measured it in the textbook and created my AutoCAD drawing of that harmonic scale. It's 3 11/16 of an inch long. That's where that number came from. Nothing magic. All right, which means that as I set this right angle triangle up, I need to know what angle this is going to be so that I can rotate it in order for the bottom to be here and the top to match up with my rise. The trigonomic formula is that angle is going to be equal to the side that is opposite of that angle, which is 2 inches, divided by the hypotenuse of the right angle triangle. If I did this number, just this, calculation on my calculator, took 2, divided it by 3.6875, that would give me a decimal number out here as the answer, 0.54237. That's not an angle. I need to use my scientific calculator and do a trigonomic function in the calculation to be able to get it to give me an angle. Which means I'm going to use something called arc sine, or negative sine, in my calculator and have my calculator calculate that out to give me an angle. So if I use this to start with, on my Texas 89, Texas Instrument 89, it's a third function. And I press that, then I put in 2 divided by 3.6875, and I get 32.84 degrees out here. So I've done the calculation for you. I'm just explaining why I'm going to rotate it at 32.84 degrees. Anybody have any questions on that? Okay. So once I do that, then I can start creating some lines. The other thing that I have to be looking at in my diagram is I now have a linear drawing of the circumference of my profile of my cam. If I take, okay, how many degrees in a circle?
360.
360. If I take the circumference length, which in this case in my diagram is totally arbitrary. If I created this plate cam in real size, the circumference of the plate cam may not end up being 12 inches. It could certainly be something else. But if I take my 12 inches, I divide it by 360 degrees, I get 0.033333 inches per degree of rotation along the circumference of my cam. Because I'm going to have to do some linear dimensions in here. Now, the more decimal places I use in this division right here, the more accurate my lengths are going to be in my horizontal length. So if I take, where did I put it? Did I put it up here? If I take, I didn't put it.
Is it at the very top?
Now, it's, in my diagram that I have a 0 to 150, I have 150 to 195, 195 to 315. So I have a certain rotation in degrees. The first rotation is 150 degrees. If I take 150 degrees times 0.033333, it's going to give me 5 inches. So my first segment is going to be 5 inches long. What probably will calculate up is 4.99999. Okay, so if I turn this 150 degrees, it's actually going to go 5 inches along the circumference. The dwell period is 45 degrees. From 150 to 195 is 45. 45 times 0.033333 is 1.5 inches. And then if I do the next one, 120 is the next segment of drop. Times this, I get 5.5 inches. And then my last period is another 1.5 inches, which will then add up to 12 inches of flat plane drawing. Okay? Those are the calculations. Already done for you, and then I'm going to verify it with the drawing itself. Whoops. Actually, I didn't change this from yesterday. That 120 degrees, somebody gave me that, is incorrect. If you actually multiply 120 by 0.3333, it comes out to be 4 inches. Need to correct that. That should be 4 inches. Because 150 degrees is 5 inches. So it can't be more than that because it's less degrees of rotation. All right. Now we go back. And look at the diagram in AutoCAD. All right, first thing I'm going to do is I'm going to rotate my harmonic scale at the degrees that I've calculated. So I'm going to do a rotate command. I'm going to use the endpoint, and it's going to be 32.84 degrees. It's going to be counterclockwise, so it's going to be a positive value. And then what I'm going to do is I'm going to put construction lines in here, because now I'm going to use horizontal segments across here. So if I do an X line from the endpoint and do horizontal and do a couple of. Now what you want to do when you're doing the AutoCAD is make sure that your node object snap is on so that it will find the point. I'm just doing horizontal lines in here at all of the increments, which was created from the scale out of the textbook for, specifically for harmonic motion. Alright, so if I back out of here, you're gonna see that these projections are lining up with the lines that have already previously been drawn. Those are my vertical divisions. And if I count them up, starting from the base, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the top. If I start horizontally from the end, I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The same number of increments vertically and horizontally. Which means that I need a line segment from here to here that is, what did we calculate that out to be? 5 inches long. If I take a line, make a line that's 5 inches long down here, I use the divide command, which is div, enter. I select that line that I just created as my object to divide, and I put in 10 segments. I can then project vertically from that they're going to line up with and the endpoint. They're going to line up and be equal numbers of increments horizontally and vertically. Everybody seen that? Then I'm going to use the spline command to create a spline. So I'm just going to click on this. And you can see that here's my intersection points. I start here at my baseline. I use this as an intersection point to create my spline. That's going to be a point. That's going to be a point. So everywhere horizontally and vertically they intersect, that's going to be a point on my spline creation. And then I'm going to stop here, create a horizontal line, and then do the same thing at the other end, only I'm going to use the uniformly accelerated and retarded motion scale, inserted into the drawing, rotated clockwise 32.84 degrees, project lines across from the points, divide that up into 10 equal increments, do my vertical, horizontal intersection points, plot my spline, finish my diagram. Any questions? So process for the left side is the same for the right side. It's just, I'm gonna probably rotate it a different angle.
Yeah, what was that tool they're using to make those lines?
I was using a construction line. It's the keystroke is XL. It's a line that has no beginning and no end. It's infinitely long. And then you can go back and you can trim them. You could use a line element. It doesn't have to be an X line. You could be a line element and snapping at the node and then coming across and just creating a line and then just trimming them out to end up with the diagram that is supposed to look like after I'm done with my diagramming, except for these. So the calculation that I made, 150 times 0.033333 gives me 4.99. So I want even increments here. 45 times 0.033333 is 1.5. 120 times 0.0333, 4 inches, and then 1.5 inches at the end. proper line weights, proper text style, font, bold font style. Don't overthink it, it's not that hard.
Do you want it dimensioned like that too, or no?
Yes,
You do want the.
I want this, again, this is a linear dimension with a text override
Okay.
to get it to say that, which is easy to do. Okay, so dwell 45 degrees, drop 120, uniform.
But you don't want the five.
I don't want the 5,
The numbers.
I don't want the numbers. No, I do not want those. It needs to look like that. And again, there's a PDF example of it on D2L, there's one over there on the board. This will be up on the screen. Title, number, scale. It can be either full or none. Question?
What's more of a helpful question? When I try to insert the harmonic scale, it doesn't like show the point style marks.
Right.
Just a straight.
Check utilities in your program and change your point style. Because AutoCAD will default to a dot when the computers get started up. At home, it probably, if you set your point style, it would remain set, but here it resets every night.
Yeah, got it.
Okay.